Now, let us look at an application of the conservation of energy equation to a closed system. We have a vessel that has a volume of 5 cubic meters. It initially contains 0.05 cubic meters of saturated liquid water, while the remaining is saturated water vapor. The saturated liquid water and saturated water vapor are existing at a pressure of 0.1 megapascal, or 100 kPa. Heat is transferred into the vessel until it is completely filled with saturated vapor, and we want to determine the amount of heat transferred during this process. For us to begin, we are going to list our state variables and how we go between our states. Starting at state 1, we see the volume of our vessel is 5 cubic meters, and we know the volume of our saturated liquid is 0.05 cubic meters. The remaining volume of our system, 4.95 cubic meters, is occupied by saturated vapor. The pressure at state 1 is equal to 0.1 megapascal. Now, we proceed from state 1 to state 2 in a constant volume as well as a constant mass process. That is, we can say the volume at state 2 is equal to the volume at state 1, and we know the quality at state 2 is equal to unity. For us to begin, we have to apply the conservation of energy equation for a closed system. Our change of energy is equal to delta Q minus delta W. Our change of energy, dE, is equal to the change of our internal energy plus the change of our kinetic energy plus the change of our potential energy. Since our system is not moving and there is no change of elevation, our change of energy is simply equal to the change of our internal energy. Since our vessel is fixed, i.e., it is not changing in volume as we add heat, delta W is equal to 0. That is, our conservation of energy equation reduces to du is equal to delta Q, or our internal energy at state 2 less our internal energy at state 1 is equal to the heat supplied going from state 1 to state 2. For us to begin, we are going to look at state 1 to determine our internal energy at state 1. Since we have enough information, i.e., we know we are existing at 100 kPa, we know the volume of our saturated liquid and saturated vapor, and we know we are existing at a saturation temperature and pressure, we can determine our masses of our saturated liquid and saturated vapor, which will allow us to determine our internal energy at state 1. For us to begin, the mass of our saturated liquid at state 1 is equal to the volume of our saturated liquid at state 1 per our specific volume of our saturated liquid at state 1. The volume of our saturated liquid at state 1 is 0.05 cubic meters, and our specific volume of our saturated liquid at state 1, i.e. nu sub F, taken at a pressure of 100 kPa, is 0.001043 meters cubed per kg. Thus, we have 47.94 kilograms of saturated liquid at state 1. To find the mass of our saturated vapor at state 1, we're going to take the volume of our saturated vapor at state 1 part of the specific volume of our saturated vapor at state 1. The volume of our saturated vapor at state 1 is 4.95 meters cubed, and the specific volume is equal to nu sub G at 100 kPa, or 1.6940 meters cubed per kg. And thus we have 2.92 kilograms of saturated vapor at state 1. With this information, we can determine our internal energy at state 1. Our internal energy at state 1 is equal to the mass of our saturated liquid at state 1 times our specific internal energy of our saturated liquid at state 1 plus the mass of our saturated vapor at state 1 times the specific internal energy of our saturated vapor at state 1. This is equal to 47.94 kilograms times 417.36 kilojoule per kg plus 2.92 kilograms times 2,506.1 kilojoule per kg. Or we have 27,326 kilojoules corresponding to our saturated liquid and saturated vapor existing at state 1. To determine our internal energy at state 2, we first need to determine our specific volume at state 2, such that we can determine what pressure we are existing at. Our specific volume at state 2 is equal to our volume at state 2 per mass at state 2. Our volume at state 2 is 5 cubic meters, and our mass is the sum of the mass of our saturated liquid and mass of our saturated vapor corresponding to state 1, or we have 50.86 kilograms. Thus, our specific volume at state 2 is 0.09831 meters cubed per kg. Now, we know that nu2 is equal to nu sub G. That is, we are existing at a quality of 1. And if we look at our saturated water pressure tables, i.e. table B.1.2 on page 782, we see that nu sub G is existing between 2000 and 2250 kPa. That is to say, our pressure has increased as we have supplied heat to transform our saturated liquid to saturated vapor. Now, we're interested in solving our saturated vapor specific internal energy, i.e. U2. Thus, we are going to interpolate between our saturated vapor specific volume and our saturated vapor specific internal energy to solve for U2. In doing such, we'd have U2 minus 2600.25 kilojoule per kg per 2601.98 minus 2600.25 kilojoule per kg would be equal to our saturated vapor specific volume corresponding to state 2, which is 0.09831 minus 0.09963 meters cubed per kg per 0.08875 minus 0.09963 meters cubed per kg. Or our specific internal energy corresponding to state 2, which is our saturated vapor specific internal energy, is equal to 2600.46 kilojoule per kg. Thus, our total internal energy at state 2 is simply equal to mass times U2, which is equal to 50.86 kilograms times 2600.46 kilojoule per kg. Or our internal energy at state 2 is equal to 132,261 kilojoules. Last but not least, to determine the heat supplied to our system, all we have to do is take the difference of internal energies at state 2 and 1. That is, Q1 to 2 would be equal to 104,935 kilojoules.